Thank you very much for introduction. I'm from RIKEN, and my name is Tarucha. So today, I would like to talk about our activities and studies using the silicon, which of course is used for semiconductor today. I'm a physicist. I may not be able to give you a very business-like presentation, but I just hope that you will feel relaxed listening to my presentation. And I would like to stick to plain language as much as possible because it's been translated. Now, at RIKEN, quantum computing is one of the major topics, and semiconductor, photon, and also semiconductor-based quantum computing are done, but also recently neutral atom and ion trap centered around the efforts by Fantium. These are also studied, but along with that, hybrid platform, which combines the power of quantum computing and HPC, is also studied to explore the new novel computational domains, including new materials, drug designs, or many body state calculations. Now, here's a question: why silicon? Why do we study silicon? When we work on quantum computing, coherence is very important. This is one of the major parameters. And in case of silicon, by using a special silicon that has the isotopically controlled 28 silicon in order to have a longer coherence time. And also because this is silicon, quantum qubit device can have the compatibility with the semiconductor manufacturing lines. And that is the reason why Intel, IMEC, and some other major silicon device manufacturers are coming into this field. Another point is, in comparison with superconducting, we can manufacture we can operate at 1 Kelvin, which is warm for us, which is hot for us. And that means the cooling power required in the refrigerator will have the capacity which is larger than in the case of superconducting by the magnitude order of 2 or more. And also, this higher temperature means that it is possible to integrate with lower temperature electronic circuits on silicon. So there's a potential that silicon-based quantum computing has a wide range of opportunities. It is well known, the characterization of the semiconductor integration technology advancement. It is named as Moore's law. You can see the number of the transistor per chip. And this trend has continued over 60 years. So when you think about that, well, actually, this shows the superconductor thing is shown with red dots, and yellow or black dots shows the increased rate of the qubits for silicon-based ones. And then the yellow ones represent our reports. So you see that the increase are the same. That means they are in line with Moore's laws. In case of silicon, we started 6-7 years after the superconducting qubits started, and that is why there's a gap. But in 20 years, we can reach like 10,000 qubits. And so far, this increase was sought after by just laying out in one dimension only, but recently two-dimensional array is being used. So if that happens, then the technology of the major vendors will be very important. Here you see examples like Intel, IMEC, Leti, and they can, so they use the bit on a quantum chip using 300 millimeter wafer. Intel uses silicon germanium. IMEC uses silicon germanium and MOS, and also Leti uses FinFET for the quantum chips. Now, just a little bit, very briefly, I would like to explain about this semiconductor quantum bit, qubit. Quantum bit, as you know, has two well-known status, and they can have the superposition. So they can have, if you create that state, then you can create a qubit. This shows the illustration of what I just said. In case of semiconductor, to make the quantum bit, you need to have upwarding and downward spins to make this status. 0 is north and 1 is south. And we put that onto this block sphere. And by using this illustration, we can express the status with this red arrow. This is the state where two arrows exist at the same time, positioned on top of each other. And the angle measured from x is theta, and the angle measured from y is phi. And manipulating quantum bit actually is manipulating these two angles, theta and phi. In case of spin, if you manipulate these angles, one way of doing that is use the technology called electronic spin resonance, electron spin resonance. For each electron spin or whole spin, you apply microwave, and the frequency of microwave matches the energy, then the spin starts to rotate. And using that rotation, the theta and phi angles can be controlled. So if you have many bits, you have to use many microwaves to manipulate the bits, qubits. The picture you see there shows 3 bits in silicon, and they are all operating, functional. So once you have these bits, how can we use them for operation? Simply put, that you have many bits, and when you conduct calculations, first you have to prepare all the qubits as starting point at 0. And then you actually perform the operation, and the result are measured in each bit to obtain the result. That is the operation. Because you have many bits, the operation will be complicated, but that complicated operation consists of single bit manipulation and 2-bit operation like AND or NOR. They are all you combine single bit operation and 2-bit operation together to create or structure very complicated operations. So you don't have to really structure very complicated operation. You actually assemble and combine single bit and 2-bit operations, and then you get the result, and that is called as readout. Now, when you do that, dynamics is very sensitive to noise, so you would have errors, and you have to correct errors in order to conduct large-scale calculation.
Because of that, when error occurs, you have to detect error and correct it. That is error correction concept. To make it easy, quantum bit operation need to be done in high precision. Error correction is equal to quantum calculation. While calculation goes on, when errors are calculated, the calculation accuracy will be lost. So same for initialization and readout. These are the minimum requirements. So the technical challenges include the fault tolerance quantum computer creation. So you have to have the very high fidelity quantum gates with good error correction. Quantum bit accuracy can be improved, and you collect all of the good qubits for calculation. So what is the precision that you need? For single bit, you need 99.9%. For 2 qubits, you need 99%. For error correction, while you have this rotation operation, when error occurs, it has to be detected and corrected. And you increase high quality bits, the number of these qubits. So the required number of qubits that can actually feel the positive impact of error correction is really the threshold that we set. So satisfy this threshold. If you have sufficient number of qubits, the bits that are used for calculation will have high accuracy. And recently, this error correction in superconductive quantum has been discussed. 17 bits or 49 bits are used to achieve highly accurate error correction. It's been reported already. If you look at the right-hand side, 49 bits, qubits, were used to create one highly accurate bit, that is logical bit, with error correction. Other than that, they are called physical qubits. To create one logical qubit. To create one single logical qubit, how many physical qubits are necessary? The number is, when you have high fidelity of the qubits, you can minimize that number. And this is the result of the calculation. Horizontally, we have various for operation. We have a physical bit number on vertical axis. If you want to achieve 10 to the minus 1, 99, or 10 to the minus 2, 99% of gate fidelity is necessary. So that would be about 150 bits. If that's 99%, 50 bit, 99.99%, you would need 20 bits, 99.99, 10. So the fidelity improvement, therefore, is a very important approach. And we have working on that for some time. For silicon quantum computing, there has been a lot of effort made. We have the fault tolerance threshold, vertical line, and horizontally years. Up until 10 years ago, natural silicon was used, so it achieved 99% line. For the past 5 years, isotope control silicon has been introduced, achieving 99.9%. And more recently, 99.999 has been the target that is set for our experiment. As you can see, the yellow highlights, 99.98% has been achieved. Lastly, I want to talk about two-dimensional array to achieve a higher number of bits. The approach has been taken by multiple institutions, 2 by 2, 2 by 4, 2 by 5, or 3 by 3. Two-dimensional arrays were created to increase the number of bits, qubits. Intel and IMEC, major semiconductor manufacturers, are using integration technologies. Sorry, the photos are dark, but 3 by 3 array on the left-hand side, and to the right you have 4 by 27 array. So number of bits have been increased due to integration, as you can see. Lastly, I want to talk about future challenges. This has been summarized in one single slide. Fault-tolerant quantum computer was a target with error correction. And necessary conditions include, we believe, is 99.99959 fidelity with error correction to create logical qubits. In terms of scaling, maybe we don't need this much as 10 to the 6th power, but to make the calculation meaningful, we believe this is a very viable target. But there are multiple technical challenges. It's not an easy target to achieve. First of all, how can we provide low temperature environments? How we achieve conditions of wiring technologies, and also the integration. Thank you. This concludes my presentation.